Okay, so we're coming to the last talk of the day, and then I think Bruce is going to give some closing remarks. So Polina Golland is going to do the final talk. Polina and I have been friends and colleagues for a long time, although I will note that 15 minutes ago she told me she hates me. But we have to forgive her, and also thank CF for being here, because they had their P41 site visit yesterday. So there's a bit of stress in the atmosphere as they constantly hit refresh to see if the scores have been posted. So there are a lot of things that I love about Polina, but two that I'll note are her sophistication and her fearlessness. She takes on problems that the rest of us want no part of. I know many of you know Adrian, who worked with 7mm emergent stroke data that scares the rest of us. Ellen Grant gives her baby data that's moving all over the place, no problem. Anyway, so it's great to have her here. She's been a friend for a long time.
Thank you. Let's see. So I feel delighted, I feel delighted to be invited to this. Thank you so much. It's great to see many of the people who I haven't seen in a while. Let's see. I should say it's strange for me that I would be invited to talk about tomorrow, because the main author on this work, the main contributor, is Adrian Dalka. I put his picture here so that you can find him in the audience. This is a collaboration with Natalia Rost and her group on main campus of MGH, the imaging stroke patients. And the way this project started is, and that's the subtitle, the way this project started is we met Natalia and her colleagues, who we were very interested in working with their data, and they said, why would you? It's terrible, nothing works on it. Freesurfer doesn't work on it. We said, okay, maybe there is something there to squeeze out. So so all of you know brain imaging, all of you know the slices. So if I look at this, so this is an example of a slice you would get from that data, and you would say, well, what's the big deal? With a little bit of work, you can get Freesurfer to work on it. The challenge is that because of the clinical constraint of imaging stroke patients in acute phase of the stroke, they skip a bunch of slices, like 6 or 7 slices for every slice that they acquire. So these slices are 1mm in plane resolution and 6mm apart. So if this is the slice that you were imagining you would see, the reality of it is that we only get to see this much as part of imaging, because again, it's every 6mm you get 1 slice. And so if you use something like linear interpolation to scale it up to normal size, this is the image you see. Because basically every algorithm in the planet that my field is responsible for, including things that make Freesurfer wonderful, rely on gradients of the image to coincide with something anatomical. These kind of images cause all of these algorithms to fail, because the gradients of these images align with the blocks that are defined by how you imaged. So they tell you much more about how you imaged rather than what you imaged. So you could smooth it, and then you lose all of the detail, and nothing aligns if you try to do, for example, spatial normalization. Or the brain masks that you estimate from skull stripping bleed into the skull, go all over, chop off half of the brain out. So what happened to us was right now So we said, that's okay, we can work with this. And so what I'll show you today is one example of what you could do with it, so that hopefully in the near future, Freesurfer can run on these images. And in particular, we developed an algorithm that reconstructs high-resolution, isotropically sampled images with anatomy that is plausible and entirely consistent with what you got to observe about the patient or the subject. And I should say that this saves about a quarter of the images that usually would completely fail spatial normalization, and as a result would be excluded from any kind of statistical analysis in the clinical studies that our collaborators are working on. Okay, so how are we going to do this? We will do it by observing that there is a lot of information within the slices, and in fact, that information is shared across all of the patients, all of the subjects. And if we had, so right now I'm illustrating it on high resolution isotropic images. In a second, I'll show you what to do with missing data. But if I had just the high resolution isotropic images, if I put a little window roughly in the location of corpus callosum, well, ventricles and corpus callosum boundary, and I put a bunch of, great, thank you. Yeah, great. So if I put a bunch of windows right around roughly the same area, we can line them up into a spatial template finally, okay. And so they're all kind of misaligned. Here we go. They're all kind of misaligned, but somewhere in here there is a patch that is very similar to one of these patches, that is kind of similar to probably one of these patches, and so on. So there are similar patches if you put them all into a bag of patches and not worry about where that patch came from. So if we do that, we get a whole collection of patches that actually have that similar structure. So for example, this patch and this patch and this patch clearly came from somewhere above the ventricles, but also grabbed some of the corpus callosum, or some, sorry, this is in the back, so some of the white matter that is around the ventricles. So what we can do is cluster these patches. In particular, we'll take the image patches that are similar and group them together and call each one of these groups that are very similar within the group and different across the groups a cluster. And so each cluster has mean of the cluster that represents a patch that sort of looks like an average patch, as well as covariance structure that tells me how often, how likely it is that if I see a bright pixel here, this pixel will also be bright, or this pixel will also be dark. So it tells us how pixels covary in these images. Okay? And you could say, well, great, but we have Freesurfer for these kind of images. The kind of images that you're talking about look like that. So what we're doing is exactly that for images that are sampled very sparsely. And in particular, we will take the patches from each image, put them in the pile, and cluster them into the clusters. So now each patch in a cluster is this very sparsely sampled patch, but the mean is dense. You could say, well, how could you get a dense mean out of these things? And the answer is lots of subjects. So if you have 100 subjects, 200 subjects, 500 subjects in your study, it means that each one of them was sparsely sampled, but in a slightly different orientation, because not every patient lies in the scanner in exactly the same way, and when you dial the acquisition, it is somewhat misaligned. Okay, and so because we have gazillion of these patches corresponding to this cluster, we could average and get the dense mean. You could say, well, but how do you know that these patches correspond to this cluster? Well, if I have the dense means, then if I look, for example, at this patch, let me give you a better example. If I look at this patch, it's much more likely to come from this cluster than from this cluster. Because if it came from this cluster, it would have much darker pixels here than here. But because it's kind of grayish, it's much more likely to come from this cluster than from this cluster. So I just described to you how, if you have estimates of dense means, you can figure out which patch belongs to which cluster. And if you have the notion of which patch belongs to which cluster, you can estimate the means. And so this is exactly what our algorithm does, but in a slightly more sophisticated, everything probabilistic way. Basically, that the patches get assigned to clusters, and even though they provide a very small amount of information, each one of them, there are so many of them that it enables us to reconstruct dense statistics of the patches. And so then, given a sparsely sampled image, so this is just a blow up of this zoom in of this image patch, I will look at this image patch, well, I will, the algorithm will, and go across the clusters and figure out which cluster had this kind of pattern that is consistent with the sparse data that is available here, and reconstruct this type of patch that gets plopped into the right location in the subject's image. And we do this patch by patch, 1 pixel at a time, and we figure out what the isotropic image is that is consistent with what you imaged and also gives you the full brain anatomy. And so how would you evaluate this? So here are some examples. So, so what we did in this experiment is we took ADNI data. Most of you are familiar with this. It's Alzheimer's Disease Neuroimaging Initiative. We took ADNI data and subsampled it to simulate what we have in the stroke imaging study. This gives us ground truth to compare against. And so the last column gives you the ground truth of what these subjects look like if you image them at 1 millimeter isotropic. Now, the non-local means and the linear interpolation completely butcher the structure of the cortex. So this is what you expect to see, and here's what you see here. They also completely destroy the geometric properties outside the brain that you might not care about as an analysis, but realistically, those are the features that are used for both spatial normalization and skull stripping. So if those don't look like you expect them to look, all the algorithms will fail. And so now is the time to say, in contrast, we get somewhat smoothed images that actually have the structure, the right structure in each of these, which makes me think, and so we're showing you just 2 examples, and we have error bars and the plots of comparing this over hundreds of subjects that prove that this does well for a large collection of images, where the gradients of the image in these imputed images align with the anatomy. Meaning that in those images, if you look at the structure here, they go from bright to dark on both sides of the fold in the same way that the highly detailed 1 millimeter resolution isotropic scan will do. As well as in the skull and the fat under the skin, they give you exactly the right geometry of the stripe, which then, of course, makes all the preprocessing work. I won't bore you with the statistical comparisons. If you'd like to see those, find Adrian and get the PDF from him. So before I conclude, and I should say, I got here in the middle of the session and everybody is giving these amazing talks that summarize 18 years of research, cutting up animals and people, imaging brains for 18 hours. I was told it's supposed to be a 20-minute talk. So I'm wrapping this up so that we can all move to the drinks. No, they were fantastic talks. So before I conclude, I would like to thank Adrian, who came up with all these ideas all the ideas in the talk, and then made them work, as well as my collaborators, Mirza Bunchu and Natalia Rost, who made this project possible in many different ways. Natalia in particular kept saying, well, but what about those other 800 subjects that don't register in our 3,000 patient study? All right, so to conclude, images are important even when they're acquired under high time pressure and with many, many slices missing. What I showed you today is a way to uplift sparsely sampled 2D stacks, effectively, is how we think of them, into full 3D isotropic resolution images that hopefully then we can apply all of the algorithms that we have available that assume that those images are as beautiful as we make them would work. And finally, this has been a fantastic event. We should uplift ourselves to the reception.